Hi everyone, today we're just going to be doing a review of the Chapter 2 practice problems from Solomon, the 11th edition. So these are just pulled from our class material in Canvas. So I'll just be going through and stopping and giving explanations. I recommend when you watch these videos that you should pause and try to solve the problem on your own, and then after you've tried it, then watch my explanation, just so that you're getting your own practice in there and you can test your knowledge. That'll be better for you. Okay, so the first one, I started my recording and then I got interrupted, so that's why we've got this weird one circled here. So I'll just go ahead and explain this to you. So the question is, which molecule does not have a dipole moment? And what they don't tell you, and I feel like it's important to know, is benzene is a planar molecule. So it's like flat in the plane of the page. And that means that the direction that the atoms are pulling the electronegativity towards is not weird like the tetrahedral ones is. It's much more intuitive. So both of these on the same side instead of in opposite directions, they'll be electronegative atoms will be pulling the electron density towards them. So if both parties were to pull equally on this pen, say this pen is electron density, and both sides of my hands are pulling equally, it's not going to go one way or the other. But if this hand is pulling more, you're going to have more electron density on that side and less on this side, right? So this side would be partially positive and this would be partially negative. And that's what's happening here in these benzene rings, is here the fluorines are pulling away from the center. So if there was a symmetry right here in the middle, both of these are pulling on the right side of the molecule. So there's going to be a partial negative on this side. This delta means partial negative, and a partial positive on this side. Okay, and then same thing here. If we draw right down the middle this way, these are pulling on opposite sides. But if you go right down the middle here, you've got this fluorine on this side pulling one way and this fluorine on the other side pulling the other way. So there's nothing canceling it out over here. There's only one fluorine on here, so that one's obviously going to be pulling off to one side of the molecule. So the only one that has even shares electrons is this. It's got the fluorines pulling exactly opposite from each other, so the partial positive and partial negative arrows just cancel each other out. So it's kind of a new application in this benzene ring, but that is something that you guys definitely went over in Gen Chem class. Okay, which molecule has a zero dipole moment? So this one is trickier because you need to know the structures of these molecules, right? So this is asking you about Lewis structures, and it's asking you about dipole moment. So which one of these has a zero dipole moment? So off the top of my head, I know the structure of carbon dioxide looks like this. But if you need to, you can go through the steps of solving a Lewis structure to figure that out. It'll just take some time, but you'll get used to seeing these molecules. I believe carbon monoxide is like this, with a lone pair on each side. And let's see. With carbon monoxide, there is a partial positive on one side and a negative on the other from the formal charge, or a positive and a negative. So that's not an ideal structure. It's not a very stable option, but it's the only one that works. So that's what we'll go with for carbon monoxide. For CHCl3, that's a tetrahedral shape. So these chlorines will all be pulling sort of down and away, leaving a partial positive. So all these have dipole moments. There's a charge on this one. So we know that CO has a dipole moment from the charge. We know that this has a dipole moment. CO2, these oxygens are pulling the electron density away from the carbons. I leave that little plus sign there so you know that what's left behind is a positive charge and the arrows are pointing towards the electrons being pulled away. So those will cancel each other out. So the only option left is, so the question is which has zero dipole moment. See, I could have gotten that wrong on a test. So this seems to have zero dipole moment. So my guess would be answer choice B based on knowing that. But let's look at SO2 also. So SO2 has a structure actually that's a little bit tricky and different. It's one of the exceptions. It can have more than 8 in its valence shell because it has access to the D suborbitals. So because of that right there, this actually has 120-degree angle between these. And with that 120-degree angle, these are pulling electron density away, and there is a heavy electron density in this lone pair. So this actually is going to be polar. So we know that CO is polar, CHCl3 is polar, and SO2 is polar, so CO2 is the only one which has zero dipole moment. So these questions, when I first started OChem, would get pretty frustrated by them because I felt like I needed to be able to very quickly make a Lewis structure and then figure out the shape of it and figure out where it was pulling. And it was kind of frustrating, but the more that you work these kind of problems, the quicker and easier it will be. And usually the nice thing about organic chemistry is you're not going to be making a million different Lewis structures of things that don't relate or anything like that. You're going to be making very similar Lewis structures over and over again. Okay, the next question is, what functional group is present in the following compound? So this is, if you know your halogens, this is a halide with the bromine right here. The rest of these are all just alkanes, just carbons and hydrogen bonded together. And with functional groups, really it's going to be easiest if you, I don't know if memorizing is the right word, but do enough problems where you recognize them really quickly. And for me, it helps to do that on flashcards. So I made flashcards for my functional groups and just memorize them. Your life is going to be a lot easier if you do. But this is a halide. So bromine, chlorine, fluorine, all those are going to be halides. Alcohols look like this. And amines, they're just OH groups. And amines are NH2 usually, bonded to a molecule. So you can go ahead and get rid of the alcohol and the amine. Now when we're looking at halides, let's talk about carbons first. So if you have a primary, secondary, or tertiary carbon, that is talking about what other carbon it's attached to. So for the primary, if this carbon right here is attached to this carbon, CH2, it's attached to one other carbon. So this is a primary carbon right here. This is a secondary. We'll get to that in a second. And this on this side, the carbon over here, is also a primary because it's only attached to one other carbon. Now a secondary right here in the middle, that is a secondary carbon because it's attached to a CH3 here and a CH3 here. So each of these is a primary and the carbon in the middle is a secondary. A tertiary carbon is attached to, that's a carbon right there, 1, 2, 3 other carbons. So once you know primary, secondary, tertiary carbons, you're looking at the alkyl halide that's on that group. So if there's an alkyl halide bonded right here, it's a primary alkyl halide because it's bonded to a primary carbon. If the alkyl halide is bonded right here, instead of this hydrogen, this would be CH2. Instead of this hydrogen, you had a fluorine. That would be a secondary. And then instead of this hydrogen, you had a chlorine, bromine, iodine. That would be a tertiary. So you're looking to see how many carbons the carbon it's attached to is bonded to. So here's our bromine. Here's the carbon it's attached to. How many carbons is that bonded to? 1, 2. So that is a secondary alkyl halide. So your answer choice is C. Now, if you had this structure with a bromine here and a CH3 group inside the ring or whatever, that would be a tertiary alkyl halide. And if you had this structure, that would be a primary alkyl halide. So that's what you're looking for, is how many carbons is the carbon it's attached to. It's kind of a weird thing. And this may seem really straightforward, but when we get to amines, they are the primary, secondary, tertiary for that is found differently. And so because of that, a lot of times students get confused. So just kind of be sure that you know the difference between these and the amines. Okay, so which of these contain tertiary carbon atoms? So that's a carbon that has 3 carbons bonded to it. And you can have a primary, secondary, tertiary, all of those in one carbon. So or in one molecule. So don't just think like, oh, this one's secondary, so it's not right. You need to look at all of these and be able to tell. So this is obviously a primary because it's only attached to one. The terminal carbon is usually attached to one other carbon. This is a secondary because it has 2 carbons on either side. This is also secondary because it has 2 carbons on either side. A lot of times people say first degree, second degree, but really the proper way to, a lot of students say that, but the proper way is primary, secondary, tertiary. If you talk to someone about a second degree carbon, they probably won't know what you're talking about. So this carbon right here has 1, 2, 3 carbons bonded to it, so that's a tertiary carbon. It also has a fluorine bonded to it, but that doesn't matter because we're not looking for how many things it's bonded to. We're looking for how many carbons it's bonded to. So answer choice 1 is the right answer. Okay. Let's see, for this one, each of these are terminal and they're each only bonded to 1. So those are all primary. This carbon is bonded to 1, 2, 3, 4, so it's quaternary. We haven't talked about that as much, but it's basically the same, quaternary. And then all of these are bonded to 2 other carbons. When they're in the chain like that, they're easy to recognize as secondary, and this terminal is primary. So we've got no tertiary here. Same thing, all these in the ring are bonded to 2 carbons, so all those are secondary. This is 1, 2, 3, 4 quaternary, so that's not going to be it. Let's see. This is terminal, so it's primary. This is promising. We've got 1, 2, 3 carbons bonded to it, so this should be tertiary. I think this one is also tertiary. 1, 2, 3. Yep, that one's also tertiary. These 2 in the ring are secondary, and this is 1, 2, also secondary. So this is another correct answer. And then, let's see, this is primary because it's got an oxygen on one side, a carbon on the other. Secondary, 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 and terminal. So primary. So the only right answer choices are answer choice 1 and answer choice 4, structure 1 and 4. So the right answer here would be answer D. It's kind of weird that it's on the next page, but okay. And for our next question, 5, that's again asking a secondary alcohol. It's hard for me to look at these in the condensed formula. And actually, I've had students before sorry, I'm just drawing that line to separate these out because it's kind of hard to tell which one goes to which. I've had students before who said they didn't do well on exams because they weren't good at practicing. They hadn't practiced much from going primary to secondary. So I want you guys to practice doing that. So I'm going to go ahead and practice doing that. So there's 1, 2, 3, 4 carbons. I'm not sure if I said this correctly just now. They hadn't practiced from going from condensed formula to bond line formula. I'm not sure if I said that or I said something else. I don't know. It's late. My brain's a little tired. So so they hadn't practiced going from condensed formula to bond line formula, so they didn't do as well on their exams. So I want you guys to practice that. So we've got 4 carbons, and on the second carbon, there's an alcohol. It's also just easier to see. And that looks like 3 carbons. 1, 2, 3, with a carbon down here and an alcohol over here. It's just easier to see if they're primary, secondary, tertiary if you've drawn them out. So we have 1, 2, 3, 4. And then answer choice D is 4 with alcohol at the end. That one looks like it's 1, 2, 3 carbons. 1, 2, 3 carbons. And oxygen and the CH3 group. Okay. So this is not an alcohol at all. This is an ether. So you can go ahead and eliminate that as long as you just know what an alcohol is. And then an alcohol, secondary, primary, tertiary, is determined the same way as an alkyl halide. It's determined by how many carbons what's the alcohol is bonded to is bonded to. So the alcohol is bonded right here. This carbon is bonded to 1, 2 carbons, so this is a secondary alcohol. So answer choice A looks like it's a right answer to me. Just to double check, I'm going to do all of them. Sometimes they have all of these, and just more practice doesn't hurt. This alcohol is bonded right here. That carbon is bonded to one other carbon, so this is a primary alcohol. This oxygen is bonded to this carbon in the middle. It has 1, 2, 3 carbons attached to it, so it's tertiary. This has 1 carbon attached to it, so it's primary. So the only right answer is answer choice A. Okay, for question 6, what functional groups are present in the following compound? So usually if you just have a plain carbon chain, no double bonds or triple bonds or anything, that's just an alkane, and we usually don't note that that's there, because that's the backbone for every organic molecule. But then if there's anything funny, funky, weird looking, I'll just circle it. So there's 2 weird things here. So one is the OH group. That's an alcohol. And it's attached to a carbon that has 1, 2 carbons attached to it, so it's secondary. And then a carbon-carbon triple bond is called an alkyne. The carbon-carbon double bond is an alkene. But we don't have one of those. I just wanted to remind you. Okay, so what we're looking for is an alkyne and a secondary alcohol. So alkyne and secondary alcohol, answer choice A looks right. I don't know. Alkyne and primary alcohol, well, we know it's not primary. An alkene is a double bond, so that can't be right. Nitrile is a different functional group that looks like this. And see, this is something I kind of want you guys to be in the habit of doing. So I'm not only going through and saying, I know what an alkyne is. I'm testing myself. Do I know for sure that what a nitrile looks like and that's wrong? Okay, yeah, I know what a nitrile looks like. And that's just another way to kind of test yourself and to use what you already know to eliminate wrong answers. And then an alkene and a secondary alcohol, well, we don't have an alkene, so the only correct answer would be answer choice A. Okay, next question, what functional groups are present in the following compound? So same thing, we've got 2 functional groups that are not just plain carbon-hydrogen chain, so I go ahead and circle them. This alcohol is bonded to a carbon right here that has 2 other carbons. So again, we have a secondary alcohol. And this chlorine is bonded to a carbon that's only bonded to 1 other carbon. So that's a primary alkyl halide. If you want to specify, it's an alkyl chloride because it's chlorine. So if it says halide, you can just replace it with alkyl fluoride, alkyl iodide, alkyl bromide, alkyl chloride. So we're looking for a primary alkyl halide and a secondary alcohol. So that should be answer choice D, I believe. Primary alcohols and secondary alkyl chloride is close, but these 2 are switched. That one almost got me. Ether and secondary alcohol. So an ether would be if this was an oxygen bonded to another oxygen. Primary alkyl chloride and primary alcohol, that's close, but the alcohol is secondary. So answer choice D is correct. Okay, so primary, secondary, and tertiary means are kind of different. So always before, we looked at what the thing was bonded to and how many carbons is that bonded to, right? It's like, where is the chlorine attached? And was that primary, secondary, or tertiary? Where is alcohol attached? And is that primary, secondary, or tertiary? Well, means are different. Amines, look at how many carbons are attached to it. So this is a tertiary. This is a secondary. And this would be a primary. So how many carbons are attached directly to the nitrogen? So you see how that's different. When we're looking at these chlorines, we're looking at the point of attachment and how many is that carbon bonded to. Well, if we did that here, if we looked at this nitrogen and see, oh, here's a point of attachment, it's bonded to 2, we would call that a secondary, and that would be wrong. This is a primary amine because there's only 1 carbon bonded to that nitrogen right there. So this is a primary amine. So this is this is solved differently. I know it's frustrating. I think if I were in charge, I would only, do, the point of attachment. But when you have a secondary amine like this, there's not a point of attachment. The nitrogen is the point of attachment. So that's why it's different. So here, there's one carbon off of that nitrogen. If we're looking at the point of attachment, it's also primary. This nitrogen has 2 carbons coming off of it, so that is a secondary. This nitrogen over here has 3 carbons coming off of it, tertiary, and this nitrogen has, just 1 carbon coming off of it, so it's a primary. So the only one with a tertiary amine is answer choice D. Okay, which compound is a ketone? All right, I'm going to give you a little hint. Anything with a carbon-oxygen double bond like that, that's called a carbonyl carbon. If it has 2 R groups on either side, that's a ketone. If it has an R group and an H, that's an aldehyde. Ketone, aldehyde. When we use these R groups, that means any carbon chain pretty much. A carboxylic acid has an OH group. And carboxylic acids are actually responsible for, if you have anti-aging creams there, and you've heard of retinols, the retinol breaks down into a carboxylic acid and helps build the collagen in your skin. So that's a little fun fact. And then this is an ester. An ester has an oxygen and then an R group. And then finally we have an amide. So these are all the different carboxylic carbonyl carbon groups, basically. And they all have little shorthands for them. So an aldehyde shorthand is CHO. There's not really one for ketone. Carboxylic acid, you'll see COOH or CO2H. So you want to recognize this. Ester is COOR usually, or CO2R. And then there's not really one for an amide. It will just look something like this. So when you see this in a structure, in a condensed formula, you know that's an aldehyde. CHO is an aldehyde. COOH, that's a carboxylic acid. And a lot of times students get ester and ether mixed up. So ether looks like this. It's just an oxygen with carbon on either side. So that ether, the way I remember it, is Esther likes cores. Esther is a girl's name, so you can say Esther, a human being, likes cores. Ether isn't a girl's name, so ether isn't a human being name. Ether can't like cores, right? So it's just the ether in the air. So if it spells out cores, it has to have a human name. So that's how I remember it. I don't know if that helps you. I'm not condoning beer or anything. It's just a little trick I use to remember the difference between ester and ether. So of all these, we're looking for one with a carbonyl carbon in the middle, C double bonded to an oxygen, and a carbon on either side with no other funny business, nothing else going on over here. But to challenge yourself, I think you guys should try to label every single one of these as ester, ether, aldehyde, amide, whatever it is. So this has the carbon double bonded to an oxygen, another oxygen over here. So that's this structure, COOH, so that's a carboxylic acid. So that's not a ketone. This looks like a ketone to me. It's got a carbon on either side of a carbon-oxygen double bond. I think B is the right answer. This has, you could go either way. I think there's an aldehyde on one side and an ester on the other. I would go with the dominant structure. So ester, it's like a bigger structure. So I'd go, that's an ester. This is definitely an aldehyde, an H on each side of that group. And then down here, this is actually just an alcohol. Let's see, the point of attachment is attached to 2 things. So secondary alcohol. So the right answer is answer choice B. The functional groups really do just go faster if you recognize them. So I'll go over some tricks like I did for this one that I have for remembering, but it's just going to be easier if you can just remember them. Just go over them and have them in your mind. Okay, so which functional groups are present in the following compound? Well, there's only two that don't look like your carbon-hydrogen backbone. This double bond is an alkene. So remember alkene, alkane, alkyne. Alkyne is triple, alkene is double, alkene is single. And then the CHO, we learned that CHO is just backwards because the point of attachment is on the right side this time. That is an aldehyde, right? The CHO forms this structure right here. If you didn't know that, you'd have to go through the steps of Lewis structure and figure it out, and it is really annoying to do. So it's easier to just start to recognize that aldehyde structure. And so see, this all would count as the R group here. So we've got an alkene and an aldehyde. So the right answer is answer choice C. So a ketone and an alkene would have been if you had this, a ketone. B, a ketone and an alkyne would need a triple bond, and triple bonds are sp hybridized, so the bond angle is 180, so they actually can't be in a ring. These need to be straight on either side, so that wouldn't work. An aldehyde and an alkyne, same thing, only there'd be a hydrogen right there. And then a primary alcohol and an alkene would be just if this was, it's close, it's tricky. Something like this, an alkene and an alcohol. CHO could easily be confused for that because there is an H and an O, but the hydrogen is directly bonded to the carbon. So, okay, so that's question 10. Question 11, the compound shown is the male sex hormone testosterone. So for all of you medical doctors, see there is an application here. In addition to cycloalkane skeleton, testosterone contains the following functional groups. So there's one right here, one right here, one right here, and one right there. Excuse me. So that looks like two ketones because they just have carbon groups on either side of them, nothing crazy. An alcohol and an alkene. And that looks like let's see, the point of attachment is attached to 1,2 carbon, so a secondary alcohol. So we're looking for a secondary alcohol, ketones, and an alkene. So all these have alkene. Oh, right there's an alkyne. So if you just know the difference between alkene and alkyne, you can improve your chances down by eliminating an answer. And then if you know what an ester looks like this. Oh, I don't know what I was doing. Apparently, I don't know what an ester looks like. And the shorthand for that is carbon, for this carbon right here, 2 oxygens and an R group. So cores, right? Ester likes cores. So we don't have one of those because there's no oxygen bonded directly next to a carbon-oxygen double bond, so that one's not right. An ether looks like this. We don't have any oxygens with an R group or carbon on either side, so that one's not right. Answer choice C has alkene, ketone, secondary alcohol. That looks right to me. But just to make sure, E just has a tertiary alcohol. We know that's secondary because we counted it up. I think 12 and 13 are the same question. I think they're just repeats. So I'm going to skip 13. But for 12, okay, this is tricky because I've seen some people circle just the carbon-oxygen double bond. But you've seen what's bonded to it can make a difference. So in this case, you have to circle what's bonded to it. And it's got an oxygen there, which makes it an ester. So that is an ester. I don't see any other functional groups present. They try to trick you here with answer choice A with an ether and a ketone, but there's not an ether because that needs to have just carbon on either side and not the carbon-oxygen double bond. You want to be as specific as possible, and ester is the combination of an ether and a ketone right next to each other, so that's more specific than calling this an ether and a ketone. Sorry, this is a little dark. The lighting in my room is like the clouds are coming over, so it's not as bright as it normally is. I'm not in my office right now, so I apologize for that, but hopefully you still find this helpful. A carbonyl and an ether. So this is a carbonyl carbon, but again, you can describe the whole structure by looking over here. You know, you don't want to say, oh, well, I could call this an ester, or we could call it an ether carbonyl. That's describing the parts, but altogether that is an ester. So that's what we're going to call it. So that one's also not correct. Carboxylic acid in an ether. So carboxylic acid looks like this. Shorthand is this. We don't see one of those, so that's wrong. So the right answer, I think, is ester. The only other thing, I can't imagine it would be anything else. For the primary alcohol, that would end in an alcohol like this. So I don't see anything that looks like anything else on that list. So the right answer should be answer choice D. Okay. For number 14, which of these is the weakest of the intermolecular forces if taken individually? So the weakest of the intermolecular attractive forces. Okay, this is something we went over in general chemistry. So this is just kind of a review. But if you remember, dispersion forces are the weakest. They're present in everything. They're actually what geckos use to climb up walls because when taken together, they can be very powerful, which I think is really cool, but not the question we're asking. So dispersion forces are present in everything and they don't have a dipole. Then there's dipole. So that's if you have two polar bonds nearby, the positive side of one will interact with the negative side of the other. That's stronger than dispersion forces, but it's not quite as strong as hydrogen bonding. And I don't know why they call it hydrogen bonding, but that's if a hydrogen is bonded to an oxygen, a fluorine, or nitrogen. My high school teacher called it H with fun. It's going to have a really strong dipole moment. Like this is really positive and this is really negative. And so if you come across another one that has this positive and negative, it's going to interact. There's going to be a really strong interaction right here between these two. And it's not quite a bond, but it's a really strong intermolecular force. So that's the strongest intermolecular force. There's the dipole and the hydrogen bonding. So covalent bonding is just a bond. It's not an intermolecular attractive force. So that's why that one doesn't count. And ion would maybe be ions being next to each other, but I would still call that closer to an actual bond. So I wouldn't take that into account. So the weakest would be the dispersion forces. Those temporarily create a dipole just by coming near to each other, but they're not truly a dipole. So they're weak, but they're present in everything. If you want to learn more about that, you can check out that episode of Chemistry for Your Life about geckos. Okay. Okay, so for question 15, we're moving right along, taking way less time than we took on chapter 1, so that's nice. For question 15, which of the following is not found in the following substance? So which of these is not present in the following substance? So I'm going to draw this out because I think it's easier to see. So ion is if you have an ionic bond. We don't have an ionic bond. So I actually think that the right answer here is probably going to be answer choice A because there's no ionic bonding. There's not a positive and a negative charge the way you would see in NaCl. So I don't think that's right. Dispersion forces are present in everything. Dipole is if you have a polar bond, and we have a polar bond right here. So if this came into contact, this is an intermolecular force, so you need it between two molecules. This bond is polar right here, pulling towards that oxygen. And so these two things aren't going to interact, but there will be a strong interaction between the negative here and the positive from that molecule. So they'll line up like this. And this positive from the polar bond will interact with the negative from this right here. So these will line up nicely together. And then hydrogen, when bonded with fluorine, oxygen, or nitrogen, creates hydrogen bonding. And again, what hydrogen bonding is essentially, it's just like a really intense dipole. It's so strong that it's an intermolecular force. It's not a bond. I don't know why they call it hydrogen bonding. Drives me crazy. It's an intermolecular force, but if this alcohol group came into contact with another alcohol group, there would be such a strong positive on this hydrogen and such a strong negative on this oxygen that they would have a really strong interaction right here. These would have a really strong interaction, almost as if it's bonded. So that makes it harder to break those molecules apart. You have to put a lot of energy in if you want to separate out this molecule from this molecule. That's what intermolecular forces are all about. They're about how two molecules interact with each other. So the only one here that doesn't apply, I guess we've got the dipole, we have hydrogen bonding, and covalent bonding is what makes up the carbon-carbon bonds when the electrons are equally shared between the two. So we have everything present except answer choice A. So A is not found in the following substance. I accidentally marked it out because I was forgetting what was not found. So I almost always get those wrong on exams. Okay, now this next question, which would you expect to have the lowest boiling point? Boiling point is all about intermolecular forces, okay? So if boiling point is about intermolecular forces, then the boiling point with no hydrogen bonding is going to be the weakest. The stronger intermolecular forces, so if these two have hydrogen bonding, they're going to be really close together. They're going to be hard to break apart. If these just have dispersion forces, they're kind of weakly bonded together. So that already apart, it's easier to separate them out and turn them from liquid into gas. Separate them out, have them take up less space, become a gas. So the one that's not going to have as strong interactions with itself, with another molecule, is this one. Okay, 17 is the opposite question, which would have the highest boiling point. These are the strongest intermolecular forces, so they're not going to want to interact. They're not going to want to separate out. So you're looking for the most hydrogen bonding. I'll just start from the bottom here. This oxygen isn't bonded to hydrogen, fluorine, or nitrogen, so it's just going to have dipole-dipole. Same thing here. The oxygen has to be bonded to the hydrogen, or the nitrogen has to be bonded to the hydrogen or the fluorine, but that's not happening here. This does have hydrogen bonding. There's an H right there bonded to an oxygen, so it could interact with another molecule really strongly. They'd have a strong interaction here. And this both don't have the hydrogen bonded to the oxygen, so answer choice C. And last but not least, because for whatever reason, 18 and 19 are the same one. For question 18, the solid alkane, C3CH2 18CH3, so that's just like a long carbon chain that goes on forever. It repeats 18 times. It looks something like that. What would it have the greatest solubility in? So this is the principle of like dissolves like. I don't know if you remember that from OChem, but you want something else nonpolar. This is a nonpolar molecule, so you want something else nonpolar. And just based on drawing the structures out for these, CCl4, that has a carbon right in the middle, has a chlorine over here, a chlorine coming out, chlorine coming out. These are all pulling opposite of each other, even though it's in the tetrahedral shape. So this is polar, so that's going to be a good candidate. You know that if there's oxygen bonded to a hydrogen, that's a strong dipole, so this is not a nonpolar compound. You know water has oxygen bonded. That's a strong dipole. Oh, I drew the arrow the wrong way. The electrons are going towards the oxygen, so that's not going to be good. Nitrogen, again, one of the more electronegative molecules, so if it's bonded to carbon, you can just kind of tell from the shape, these don't look like they're going to be even. The nitrogen's pulling away from the CH3. And then having an oxygen makes it polar. So the best option is going to be the least polar one, and that is going to be CL4. So answer choice A. I hope this was helpful for you guys, and good luck studying for your exam, and please feel free to reach out if you have any questions.